There we go. And let's get started. All right, welcome back, guys. How was spring break? By the way, your midterms are up here. If you want to pick it up, we're about to go over the midterm. Tobiah. Yeah, how was spring break, guys? Did you guys enjoy it right after the midterm? Good break afterwards. Okay. All right, so here is it's just 3 separate stacks. I think they're all sorted by first name, I think. So you're looking for, I think this is here, right?
Yeah.
Okay. Okay, let me stop my video. Okay. Got it. All right, so let's pick up your midterms. I'm gonna leave open the opportunity for you guys to do corrections to get up to, the corrections are gonna be due on Friday. So you have between now and Friday. We're gonna go over the midterm in class today. So if you've got a pen handy, you might wanna do corrections as we go over the midterm. You can get up to half of the points back for your corrections. And yeah, I'm going to make them do 318. Just use pen to correct them, and I'll regrade them once you give them back to us. Any questions on that? Yeah. You need to provide a short explanation as to the answer. Right. So for the algorithm ones, you can, yeah, I think a good number of them ask you to justify. So those, it's included as part of it. But even for this true false, you need to write like a sentence or something, like a short sentence explaining why the answer is the way it is. Okay. Does that make sense to everyone for corrections? Great. Also, FYI, homework 6 has been released. It's due next Wednesday. The written part of homework 6 is on graphs. This is the first time we do some written graphs. It should be, I think, fairly straightforward, hopefully. And the coding portion is actually, you guys are going to be implementing the algorithms from the midterm. That's your coding portion. So again, this lecture should be very helpful for that. And knowing the solutions and pseudocode should be helpful for that, right? Cool. All right, so let's get started. All right, so the first thing I'm going to do, I'm going to review the grade distribution so you guys know where you stand. So this was the overall distribution for raw points. So the midterm was graded out of 88 points with a possibility for 5 bonus points. Actually, 10 bonus points. I will say nobody attempted the bonus question at the end. I think the midterm was too long by 1 question. All right, so that's what I've learned giving this midterm. And then, yeah, so this is the overall distribution. Seems like the middle-ish area was like 50 something. So if you got around 50 points, that means you are around the middle of the class, right? I curved, so this is how the grades are curved. Your grades on Blackboard are your official grades currently. If you do corrections, your grade can be brought up, okay? So anybody who got an above 74 was given an A, and then they were curved within that bucket. Okay, so an A in this case is like 90, I think 94% up or something like that. Yeah. Anyone above 64 was given an A minus, above 54 a B plus, above 41 a B, above 31 a B minus, and then there were the rest of you are in this bucket. Okay. I won't go into detail into all of them. The buckets get a little bit smaller towards the bottom, but there are a lot of like FD. Yeah, we had the whole range. We had people on the F side. We had people who, nobody got a perfect score, but there were people that were very close. All right, any questions on the distribution? And so again, your grade on Blackboard is going to be this curved grade, but this is how I'm roughly mapping the raw score to a letter grade. And then the letter grades are described in the syllabus as to like how they map back to percentages. Yeah. Oh yeah. Should be somewhere in the stack. Feel free to pick it up. Oh. You can email it. Yeah. I printed it. I just didn't pick it up. Okay, I think. Yeah. I'll email it to you. Okay. Yeah. Cool. Any questions on the distribution? How are you guys feeling? Are people happy with their grades? Unhappy? Unexpected? Wait, very happy. Oh, I didn't want very happy. I wanted like the normal, like the students that normally get B's to get B's. Is that, do you guys feel like that's the case? If you're a B student, you got a B? Yeah. Okay. No, maybe. Okay. No. Okay. Well, that's what the curve ended up being. You do have an opportunity if you make corrections. I actually looked at everybody's grades. If you make corrections, I think the most you can get bumped up is by 2 half-letter grades or whatever. So there are some students, especially towards the bottom, if you do corrections, you can go from B- to like B+, essentially. So I encourage you to do that. Okay, so let's take a look at the midterm. Let's get started. So question 1. Oh, sorry, overall statistics. The median was 40. This is some other stuff you guys probably don't care about, but you can look at it later. All right, so section 1, the median here was 5. The question was graded out of 10 points. There was somebody that got 10 points. This is what the distribution looks like for this question. So this gives you a sense of whether you know this material or not, right? All right, question 1 was order following complexity classes from smallest to largest. I hope you guys had this in mind when you were thinking about it, but let's just do it as a class. Who can get me started? What is the smallest complexity class? O of 1. Okay, so this is 1. What comes next? O of log n. Yes. X. Yes. Cubed root of n comes after. Okay, so this is 3. What comes next? N log n. This is slightly grows faster than just cube root of n. You can think of this as growing slower than n, right? What's next? So what's after n log n? N cubed. Okay. What's after that? 3 to the n. Yes. What's after that? N factorial, and then the last one is n to the n. Does that sound right? Oh, I see. Well, do whichever one is on the test. This might be a different version of the exam. There were several versions for people that couldn't take it. So what is on the O of n is on the exam? Oh, okay. All right, so that's question 1. Any questions? That should have taken you guys 30 seconds to do on the exam at most. Okay. Yeah.
On my paper, it says n log n and then O to the n raised to the n and factorial was the last one.
If there are mistakes in the grading, email me or come talk to me at office hours. Yeah. So if you have specific questions about your exam, just come like schedule some time to talk to me during office hours. All right, next question. Simplify n log n. What's the answer here? Yep, n squared. And why? Again, this is what we're trying to get at with big O, right? So if I plug in n equals 1,000,000, n log n is this, 6 million. N squared is 1 trillion, okay? Square root of n is 1,000, and then this is just constant, right? So when you add them up, this is the answer you get, which really means, really the only thing that matters is that this is about 1 trillion, right? So that's why the answer for this one would be O of n squared, because it is the biggest term that grows the fastest, that matters the most. So when n gets really large, everything else doesn't matter. Cool, great. All right, true, false. N is theta of this other thing. What's the answer here?
False.
False, why? What does theta mean? Big theta. Yeah, it means it's both upper bounded and lower bounded. So if I asked you, is n big O of n log n plus 200 n squared. What would this be? Is that true or false? This is true, okay? Because n is smaller than or equal to, basically, right? Now, if I ask you, is n big omega of n log n plus 200 n squared? What is this? Yeah, this one is false because it's asking you, is n bigger than or equal to this, which it's not, right? Because n squared is much bigger. So since one of these is false, beta has to be false. Beta means both, right? Means about equal. Great. And that's what I had on the slides. This is false. What about this one? I think it's multiple choice. Right. What was the answer here? Yeah, Jonathan. Right. C is big omega of A. Why? Because A is big O of B, which means A is less than or equal to B. B is big O of C, which means B is less than or equal to C, which then means A is greater than or is less than or equal to C, which is the same as C being greater than or equal to A. So C is big omega of A. Right. And again, the only thing you wanted to remember here is you just needed to remember these rules of thumb. Okay. What is big O? What is big omega, etc. Again, upper bounds, lower bounds, and then tight bounds for big theta. Any questions so far? I was a little disappointed in this section. I really thought people were going to get a lot more points because these are fact. These are like just fact based. Okay. All right. Section 2. I believe this was out of 6 points, and it looks like the median was 3. And so just keep that in mind. So we have 2 algorithms, Alice and Bob, and they got 2 proposals for 2 sum Alice and 2 sum Bob. Now, this should have reminded you of a homework assignment that you guys did for figuring out the cost of the pets. I think homework 1, homework 0, something like that. Now, most of you did this implementation in your homework. So this should have been like, I read that, reminds me of something I wrote, I can probably figure out. So what is the running time of this implementation? N squared, right? You have one for loop here going n, you have one for loop here going n. You do constant work here. So this is O of 1. Returning true is O of 1. This is this loop is O of n, and this loop is O of n. Because they're nested, that gives you a total running time of O n squared. How much space are you using? O of 1, right? So we never count the input space, right? Otherwise everything would be O of n. We never count the input space. But in addition, like how much extra variables you're using? Well, you're defining an I, you're defining a j, and I think that's it, right? So you have a constant number of variables. You have 2, 3, 4 of extra space. So the time is n squared. The space is O1. Now this algorithm is better, faster. Who wants to take a stab at the running time? Yeah, Vincent? Yeah, O of n. Can you explain why? Right, so you have one for loop here, which is going from 0 to n minus 1. So that's about O of n. And then inside the for loop, you're subtracting and setting equal. So that's basically O of 1, just 3, 4 operations, right? You're checking to see if seen before dot count is equal other add-in equals to 1. This is tricky. You need to remember that because this is a hash set, figuring out if something exists in the hash set is O of 1 as well. So looking up in a hash set is constant time. Returning true is O of 1, obviously. Adding into a hash set is also O of 1. And indexing into a vector is O of 1. So you have a bunch of O of 1 stuff inside. They're all O of 1, and you have like 5 of them. So it's like O of 5, which is O of 1. And you have one for loop. So that means your running time is O of n. So this algorithm is much faster than this one, right? So if I give it a vector that's the size of 1,000,000, this is going to take 1,000,000,000,000 operations. This is only going to take 1,000,000, right? What's the trade-off? What about the space? Yeah, Serena? Yes, the space is also O of n, because in this case, we have this variable called seen before, which, if you notice, we add every element of the vector into that variable, right? So in the worst case, it'll be the size of the vector. In the best case, if the vector is all ones, it'll be size 1. But again, we're always thinking about the worst case. All right. And I think those were the 2 questions for 6 points. Any questions? That probably should have taken you guys a minute or 2 minutes at most. Okay. Obviously, yes. All right. So section 3 was out of 10 points, and you guys did very poorly in this section, which is not unexpected because I think this was the first time I asked you guys to do some pseudocode. So if you did well in this section, if you're one of these people, you're doing great. Okay, keep up the good work. If you have not seen this problem before and you're one of those people, you're just doing amazing. Okay. If you're somewhere here, like in the 6 and the 8s, you're doing pretty well. Okay. All right, so let's take a look. So this was the problem. Write out the pseudocode and runtime for an algorithm to find the smallest missing element in an array, in a sorted array of non-negative distinct integers. All right. For full credit, I needed your algorithm to be O of log n. Okay. What is an obvious O of n algorithm? Yeah, O of n. What is a brute force algorithm for this problem? Right. So within 30 seconds to a minute, you should have realized that one way to solve this problem is just start at the beginning and check if the next element is +1. You know, and every time you check if it's +1. If it's not +1, then return the previous element +1 because that's the one that's missing. Okay. That works in all cases, and it's O of n, pretty fast. All right. That would have given you, I think if you did that and you justified your runtime, you should have gotten 7 points in this question. Okay. Now, let's go through a few examples to see what you might be able to do better, which is, this is one of the examples I gave you. The missing element is 3. Okay. This is the brute force algorithm for pseudocode that we just discussed. Yeah, so you can write on this, huh? Okay, interesting. This is what the pseudocode would look like, right? If your array is empty, the answer is 0 by default. Okay. Otherwise, you go from 1 to n-1. If you're off by 1 in the indices, you didn't get points off. Again, you guys, okay, this is, you're not going to implement this in your homework. Your homework, you need to implement the log n solution. But here's all you had to write to get, 5 points, and then you needed to justify that this was O of n, which you could just say like, there's a for loop and I do constant work, right? So that would have given you 7 points, couple lines of code. Obviously, it's hard because you're in a test. It's a lot of pressure. But I was hoping more folks would provide this solution. All right. Now, when you look at O of n, one thing that we've learned in class is divide and conquer. So you should think of trying to use that technique to help you improve your algorithm. Okay. So what you do there is we think through a few examples. How can I divide this array into pieces that help me solve the overall problem? So something to think here is, well, a very natural way to divide arrays is to look at the middle. Okay, so anytime you see arrays, anytime you see divide and conquer, you should think, well, maybe I can divide into the middle, right? So if I look at the middle here, I notice that this array is missing 0, 1, 2, 3. This array is missing 4, right? So this is the input I'm given at the top. All right. This is what the array should look like if it was correct, right? If it was missing no numbers until the very last one, this is what it should look like, right? So if I look at the middle, there's a few cases to consider. In this case, the 3 equals the 3. Okay. So this value is, look at the middle of my array, a n over 2, right? So just look at the middle. This value is take whatever I started with and add n divided by 2 to it, right? That's how I get 3, because I'm at 0, I add 1, I add 2, I add 3, right? So we're going to use that information to consider this case. So in one case, these two values are equal to each other. What does that tell you about where the missing array, where the missing number is, if they're equal?
Not on the left side.
It's not on the left side. It has to be on the right side, right? So if you're using the divide and conquer approach, you would say, if they're equal, call myself on the right side and try to find the missing number there, okay? Here's another case, so you should consider. So here's the case where this value is bigger than the value it should be. What does that tell you? That the missing value is on the left side, okay? So now you figure out, hey, if I look at the middle, if they're equal, it tells me I only need to look at the right side. If the mid value is bigger than this formula, which I can compute in constant time, I need to go look at the left side. What's the other case? There's this case 3, which is saying if this number is smaller than the number I wanted, okay? Now, why is this impossible? Or like, why is this a case you're not going to run into? Yeah.
You gave us non-negative values.
Right. The only way this would happen and the array still be sorted with distinct integers is if you have a negative value at the beginning of your array. So this case actually never happens and can never happen. Okay. So you actually don't even care about this case. But that gives you the pseudocode for your algorithm. So once you realize that, which is look at the middle, and then I'll either go left or I'll go right, you can just write it in pseudocode. This is your base case. If my array is empty, return 0. You should always have a base case. This is another interesting base case. I think I gave points for either of these base cases. You do need both. This is the algorithm you will have to code in your homework for homework 6. Okay, so you should understand why this base case is needed. But this is the case 1 we just talked about. Look at the middle. If it's equal to this value, then go to the left. Oh, sorry, go to the right. Sorry, this syntax means go to the right because you start here and you go all the way to the end. Otherwise, you're in case 2, which is go to the left. Okay. This is actually a very similar definition of binary search. If you've ever seen that in a recursive fashion, it's basically the same code, except the if statement is different. Okay. So again, we can walk through an example to make sure that this works. You didn't have to do this on the test. You know, if you have the right idea, you're going to get credit. But if you want to convince yourself this works, let's walk through an example. So this is our example, 1, 2, 5, 10, 14. What's the missing number? So the answer should be 3. Okay. So first, we're going to walk through the code. So we don't hit either of our base cases because this array is of size 5. So what we're going to do is we're going to look at the middle, which is 5. What are we comparing 5 to? No, you're comparing it. It should be 1, 2, 3, right? So you're comparing it to 3, right? So that's what this is doing. So this is saying is 5 less than or equal to 3? The answer is no. So it goes this way, it goes to the left. Okay. So it goes to 1, 2, and then it repeats itself, right? So again, we don't hit a base case because this array is too big. So we look at the middle, quote unquote. So this is size 2. So 2 divided by 2 is 1. So we look at the value at index 1. Okay. What does 2 get compared to? It gets compared to 2, right? 1, 2. So it asks, is 2 equal to 2, which is yes. So it calls itself on the right-hand side of the array, right? So it calls itself on 2 just by itself. Okay. Now 2 hits a base case, which is this one, and it says return A0 plus 1. So return 3, right? And that is, and then everything just returns up, right? It just returns that answer back up to stack. So it does give us 3. So again, you didn't have to do this on the exam, but if you were curious, so when you're taking the test, you want to like, this is enough. Just having the right idea is enough. If you code it up and you're like, for some reason it's not working, because it is very important that you like get like, a lot of times you'll get like off by 1 errors. So this n divided by 2, this n divided by 2. In pseudo code, we usually don't care too much. We just say like, you'll figure it out when you're actually coding it. But if you're getting the wrong answer, but you have the right idea, you probably have an off by 1 somewhere. You're like accidentally like forgetting the 5. And you're like, when you say like cut in half, you're like accidentally looking this way and accidentally looking this way. And like the 5 got forgotten, right? Or something like that. Okay. There's a couple more examples on the slide, so we can walk through this one. So again, we look at the middle. What is this 3 being compared to? 3, right? So it's equal, which means I hit the first case. So I go look at the right, 3, 5, 8, 10. Okay. When I look at this, I look at the middle. So again, by our definition, the middle is always the one off to the right, just the way I wrote the pseudocode. You can implement it in a way where it's off to the left, but you're gonna like the plus minus ones are gonna change a little bit. Okay. So I look at 8. What do I compare 8 to? 5, right? Because I compare it to, I think it should be 3, 4, 5. It's actually 8, right? So I compare it to 8 to 5, which means I'm actually going to go over to the left side, 3, 5. I'm going to repeat this. I'm going to look at 5. I'm going to compare that to 4, which is 5 is bigger. So I'm going to go over to the left side again. And now I hit a base case. And in that case, I'm going to return 4, which is actually the answer to this problem, right? So it does work, right? Cool. There's more examples in the slides. We're going to skip this one. Question is, how fast is it? What is the running time of this algorithm? I mean, I did give it to you in the question, but how would you argue that the running time is log n? Yeah, every time you call yourself, you're splitting the array in half, okay? And ignoring the calls to yourself, all you're really doing is like adding 1 and doing a comparison. So there are, how many times can you call yourself? Log n, because every time you split in half, and you can only split yourself in half log n times, right? And each time you call yourself, you do about constant work. So running time is log n. Another way to do it is you can use master theorem. The recurrence for this is T of n equals T of n divided by 2 plus O of 1, because you do constant work. By master theorem, the running time is log n. Cool. Any questions on that section? You will be implementing this algorithm in your homework sets. C++ or Python, whatever you want. Cool. All right, section 4. Pretty good. You guys did pretty good in this one. I'm not too unhappy about it. True, false. For arbitrarily comparable objects, we can design a stable algorithm that has worst case O of n running time. Again, this is just, everyone should have gotten this. We talked about it in class. This is just a fact-based question. But a lot of people didn't get it, so it's okay. We will review it. What is the true, false? Who wants to give it a stab? False, okay? So we talked about this. Okay, there are O of n algorithms, such as radix sort and counting sort, okay? But they are not comparison based, right? They use the fact that you're sorting numbers, that you're sorting things you can hash, okay? In order to get fast running times, right? So you could say this is kind of a trick question because we did cover O of n algorithms, but I guess the main thing is these algorithms assume that your objects are hashable, whereas everything else does not. They just need to know is A bigger than B. That's all they need to know. They don't need to be able to put into buckets. Yeah.
So the phrase arbitrarily comparable means that like it's not hashable, or that means that it has simply numbers?
Yeah, it just means that it's not, the only thing you know about the objects is that you can compare them. That's the only thing you know. So what this question is saying, if I have elements I'm trying to sort, and the only thing I can do to them is compare them, can I have an algorithm that is O of n time? And the answer is, if the only thing you know about them is you can compare them, the answer is no, you cannot. Now, if your objects are integers, then yeah, obviously you can do radix sort, counting sort, right? If they're strings, you can do these as well, right? Yeah. So this is false. When using a random pivot, the expected running time of quicksort is n log n. True, false?
True.
This is true. So again, we had a whole lecture on this, so I hope most of you got this as true. All right, this was a more interesting question. A lot of folks made progress on this one. But again, we have given an array of integers, find a contiguous subarray with the maximum possible sum. Okay. The entries of the array might be positive or negative, and here's a few examples. So again, for this example, the answer is 15 because 4 plus 11 gives you 15, which is the biggest possible sum you can get from any numbers in the array that are next to each other, right? So that's what contiguous means. It means they're next to each other. Okay. You can look at the other examples as well. But I guess the first question asks you, like, how would you solve this in a brute force fashion? Or like, what is just an algorithm that you can sort of think of to try to solve this problem? Yeah, Leander? Yeah, so you can actually just try, essentially the idea would be, you're trying to find the biggest possible sum of contiguous subarrays. So the idea would be like, let's try all the possible subarrays from I to j, right? And for each one, we can compute the sum, and then we'll just take the maximum of whatever we ended up computing, right? So the idea there would be like, well, this is a contiguous subarray that starts at 0, ends at 1. Its sum is -10, right? This is the next subarray, starts at 0, ends at 2. Its sum is -6, right? This one starts at 0, ends at 3. Its sum is 5, right? So you can imagine trying all of these. So essentially, for all subarrays that start at 0, try all of the ending points. Keep track of the sum, okay? Then move on to the ones that start at 1. Try all the ending points. Keep track of the sum, right? Then move on to all the ones that start at 2. Try all the ending points. Keep track of the sum. Move on to the ones that start at 4. Track all the ending points, the ones that start at 1. And then finally, if you remember, there is an empty subarray that has sum 0, let's just say. Okay. So the first question was, in plain English, describe a brute force solution to the above problem and the running time of the solution. So the solution we just went over is what we would call the brute force solution. Okay, it's not clever. It's not trying to be smart. It's not trying to do anything super clever. It's just saying, you want the maximum possible sum of subarrays? Sure, I'll try all of them. I'll compute the sum for all of them, and then I'll give you the maximum one. Okay, so depending on how you implement it, the running time can be either n cubed or n squared. Okay. Here's the pseudocode for one of the implementations, right? So again, from I to 0 to n-1, from j to I, from j equal to I to n-1, right? Compute the sum in another loop, and then keep track of the maximum. Okay. What's the running time of this pseudocode implementation? Yeah. This one's n cubed. This one. This is another implementation that a lot of you probably jumped to. So again, start from I to 0 to n, j equal to I to n-1. and then you reuse your sums as you go along. So instead of computing the sum of the subarray fresh every time, which is what you do here, right? We always started at 0 and we recompute it. Here, you take advantage of like, wait, I just need to like add the next one and that gives me the next sum, right? Like I don't have to start all the way from I can just add the j. What's the running time of that one? O(n squared. So I would say, I personally would call this one the brute force, because this is just, don't think about it, just do it. I think this one's a little clever. Okay, so you should feel good if you thought of that one. You already went from n cubed to n squared. You went from like array of size 1,000. Okay, n cubed, that's going to be a trillion. No, a billion. That's a billion. N squared is only going to be a million. Okay, so you're already going from Jeff Bezos to like your everyday middle class American, right? All right. Now, the next question asks you the maximum sum subarray. Okay, so whichever array it is, right? It can either be on the left side or on the right side. Okay. Or what's the third possible case? It includes the middle value. Okay, the third possible case is it has to include the middle value. It like crosses both. Okay, that's what this question was asking. This is an example of where the maximum one, the maximum possible is actually 10 plus 2 plus -1 plus 5 plus 8, which I think gives you 24. That's the biggest possible. Okay, part of the reason is that this side has 12, this side has 13, and the -1 is not negative enough to like split them. You actually want to take the -1 because then you can add 13 and 12. Yeah. No, because you don't want to take the -4 and this -4. They will only subtract from your sum, right? So you don't want to take those. Cool. What about this one? What is the maximum possible subarray for this one? It's actually here. It's 12, right? Why can we not take the 5 and the 6, which is 11? Because the -20 is too negative, right? In order to take this 11, like to include it, we have to also include the -20, which undoes the, the 11, basically. What about this one? So the other option here, actually, this is 12. And what is this? This is 15. So again, similar argument. You have 15 here. You have 12 on this side. You would want to take the 12, but the -20 is too negative. So you don't, right? So these are the three cases. Either your answer is on the left side, it's on the right side, or it's somewhere that includes the middle. Okay. So that should give you a hint. Like it's either on the left, on the right, or on the middle. So again, we covered divide and conquer in class, which means how should we approach this with the divide and conquer? So here's an example where what I'm doing every time is I'm splitting the array in halves. Okay. So this is the left side, the right side. For this array, this is the left, the right. For this array, this is the left, the right. Okay. So it's just splitting everything in halves every time. And then you can ask, well, once I've gotten to the bottom, for each of these arrays, what is the maximum possible sum subarray? Right. So for -4, what is the max possible sum? It's 0, actually, because you can take the empty subarray. Okay. So this one is 0. This one is 10. This one is 2. This is -20. This is 5. This is 6. This is negative. This is 0. Okay. These are your base cases, right? Because when you have an array of size 1, it's obvious what the answer is. Okay. Now, the question you ask yourself for divide and conquer algorithms is, if I have the answer to the smaller problems, how can I figure out the answer to the bigger problems? So for this array, I have -4 and 10. I know the answer to the left side is 0. I know the answer to the right side is 10. What is the answer to that array? So it is again 10, right? The maximum subarray I can have is just 10 itself, even though I have the -4, right? You can think through, I think for all of them, this one's also 2. This one is just by itself, so it's 5 again. This one's also 6, okay? But you keep going, which is, okay, well, now I know the answers to this side and this side. How can I use those answers to help me figure out the answer for the whole thing? Yeah. Oh yeah, this should be a 0. Yeah, you're right. That is bonus points for you. That is actually a bug. Yes, that should be a 0. But I think the main thing is, if you know this side is 10 and you know this side is 2, what is the maximum subarray for this one? It's actually 12, right? So it's that third case where from this side you had 10 coming up, so it might be 10. From this side you had 2 coming up, so it might be 2. But you realize, wait, actually, if I take the one across the middle, that's bigger. That's 12, okay? So this one actually gives you 12. And again, it's the same thing for this one, which is you might think it's 5, or you might think it's just 6. But actually, it's the one that has both arrays. It's 11, okay? And then similarly, at the very end, you actually figure out it's actually just 12. It's this side. Because if you try to take the one that has the middle, you take the -20, which screws you. Let's see. Right. So the other tricky part here is essentially computing the third case, which is if I'm in the middle, right? How do I actually compute the maximum subarray from the middle, knowing that it's in the middle? So you might think like, oh, that's the same problem I'm trying to solve. So like it's kind of difficult to do. Actually, it's a much easier problem because you know you have to have the middle value. So what you would do is you would start with your middle value, -20, and then start going towards the right. Or towards the left. Okay, these slides are a little off, but essentially you go towards the left, computing the running sum, okay? To figure out which one is the biggest that you got. So the biggest possible here was -8. And then you repeat the same thing for this side. And it turns out the biggest possible was 11, which means the biggest possible, including middle, is -8 plus 11, which is 3. That's a little probably hard to explain. This is the pseudocode. This problem is a lot more complicated. If you got, I think the only part, we took off like 1 point if you didn't get this part, which is the hard part, or like the tricky part, okay? This is the part where I'm trying to compute the middle maximum, okay? This part is just call myself on the left, call myself on the right. This part at the end is just take the max of the left, take the max of the right, and then take the max of the middle. This for loop is the one that's trying to compute the middle one, okay? What's the running time of this algorithm? Yeah, so I did give you the answer, which is n log n. But how would you figure out what the running time is? Right. You can use master theorem, which is you call yourself twice on the left and the right every time. And then this for loop is O of n. So in addition to calling yourself, you do O of n work. So by master theorem, this is n log n. Cool. Wow. All right, so the midterm was hard, I guess. Section 5. You guys did really well in this section. So let's go really quickly through it. We have a few more minutes. What's the value of the root? What's the value of the leaves? So the root is 2. The leaves are 6, 8, 5, 19, 33. A lot of you missed the 26. I think we might have given full credit for that anyway, but just, you know. If we run DFS starting at the root, which value is going to have the largest finish time? The 2, because you start it at 2 and it'll finish when everything is finished, right? So the 2. What's the longest path from the root to a leaf? I think most of you got this, which is 2, 7, 10, 1, 19. Okay. This one also, I think most of you got. So this is just trying to define a tree in code. What does the tree look like? It looks like this, okay? You have the 3, you have 2 children, -2 and 10. And then the -2 has 2 children, -5 and 0. And the 10 has 2 children, 5 and 12. Okay. Is this tree a binary search tree? The answer is yes. This is smaller than -2. This is bigger than -2. This is smaller than 10. That is bigger than 10. This whole tree is less than 3. That whole tree is bigger than 3. Section 6. Minimum of the tree with recursion. I have a lot of slides for this one, but I think the answer is pretty straightforward. Who wants to give it a shot? I'm trying to find the minimum of an entire tree recursively. And I have a for loop going over each of the children. Yeah. Yeah, so essentially using recursion, what you want to do is your min so far is your current value. So you would say min so far is equal to the minimum of your current minimum so far, and then calculate the minimum of the child, which you can do using yourself. Find min of tree on child. Right? That's about it for this one. That was worth 4 points. There's an example in the slides where you can walk through to make sure that it works. But basically, you keep calling yourself until you get to 19, and then you're like, oh, the minimum is 19. And then you say, well, what's the minimum of the other trees? Oh, for this tree, it's 5. For this tree, it's 1, because 1 and 19 are smaller. 5 is just by itself. And then it basically bubbles back up until you get the minimum, which is -3, which is here. Okay. Yep. Okay. Question 19. We have a few, just one more minute. Any breadth first traversal of this tree? So what is breadth first traversal? Breadth first. Breadth first. Breadth. A lot of you did depth first search, but basically anything that had the nodes like start with 10, and then these can be in any order you want. So let's say 4 and then 27. These can be in any order you want, but they all have to be after 4 and 27, right? Because breadth first means you go level by level. Okay. If we search for 26, what is the value of the last non-null node that will be visited? Well, you look at 10. Is 26 bigger than 10? Yes. So you go to the right. You look at 27. Is 26 bigger than 27? No. So you go to the left. You look at 17. Is 17 bigger than 26? The answer, or is 26 bigger than 17? The answer is yes. So you would go to the right, but then you hit a null, which means the last one you saw was 17. Right? Just binary, just search on a tree. If we insert 7, will the new node be a left child or right child? So again, is 7 bigger than 10? No. So you go to the left. Is 7 bigger than 4? Yes. So you go to the right. Is 7 bigger than 6? Yes. So you go to the right. Is 7 bigger than 8? No. So you insert it on the left. Cool. For this one, finding the height of a tree, this was kind of a trick question. For both of them, it's O of n. And section 7 is kind of long. So I will record a video to go over the section 7 solution. This is the question I think I should have left out of the midterm. Clearly, it's a little long. It is not hard, I would say, but clearly a lot of you didn't even get to it. So yeah. And then the last one, if you guys want to stay just for a few minutes. Well, I guess we're at time. So what I'm going to do is I'm going to record the last two, so section 7 and section 8, and I'll post them online in addition to the current recording. Yeah. Yeah, you should take these home. It's fine. Do the corrections on them with like paper with pen. Bring them back on Friday so I can grade it and then give you half points. Yeah. Huh? Yeah. It's already on the website. Yeah. So for you guys, if you the PowerPoint itself, if you go to lecture 21, midterm overview, here is the PowerPoint is these links. Okay. Cool. All right, thanks everybody on Zoom. I will be disconnecting now. And then, yeah, if you want, please come pick up your midterms. Is it asking for permission? What's asking for permission? I'm gonna stop sharing. All right, folks on Zoom, please come pick up your midterms in my office. If you get it, oh, to the slides. Okay, I will grab. Good point. Yes, on your test. Yeah, and then just correct it there and include a justification. Yeah. Okay, the slide should be public now. Yeah. A blank one. Yeah, you can take it if you want. Sure. Thanks, Jordan. The slides are now public. Sorry about that.